are discussing the Cn beta effect because of vertical tail for wing and then fuselage. As I have told you, for the fuselage, we will be discussing all the longitudinal case or directional case in one lecture only, because it needs different approach, mostly empirical formula you have to use. So I will not be computing Cn beta because of fuselage here. I will not try to model it. We will do it in one lecture where longitudinal, lateral, direction all will be modeled. But vertical tail we have seen, say Cn beta greater than 0. We also know how to calculate Cn beta. Now we are thinking about wing. Let us say wing contribution. Right? Wing contribution towards Cn beta. Let us understand first the physics, why there should be a Cn beta contribution from the wing. Meaning thereby, if the airplane is going like this, if there is a side slip, angle introduced because of disturbance, why should wing try to generate yawing moment either this way or that way? We are talking about the wing, not the vertical tail, talking about the wing. Right? So let us take a general wing. And by now you understand this is a relative V, so this is positive beta, okay, because relative wind is coming from the right hand side. Now we are flying like this. So now you could see one thing very clearly. If you see this diagram, if velocity was like this, it was going like this, then the normal component to this leading edge, okay, because this is a sweep, this is a swept wing, and in swept wing, you know, you will get the desired effect through installing the aerofoil contouring in a particular fashion. For example, let me clarify what is the sweep so that you do not get confused between sweep and taper ratio. And it's very, very important understanding, and you must understand. Suppose this is the plan form of a wing, and these are the way the aerofoil shape has been contoured. Okay. And if there is relative airspeed V, then do I call that this airplane is having a sweep or not? Should I tell this is having a sweep in a literary sense? The question is yes or no. So let us see what is the physics behind or philosophy behind a sweep. The understanding was, suppose this is the rectangular wing and this is the free stream relative air speed. Okay? We understand one thing. Most of the forces that is generated over an wing is because of the normal component of velocity, which is on the leading, start from the leading edge like this, okay? On the normal component to the leading edge that decides the majority of the forces. So now if I give a shape like this and still the aerofoils are kept like this, then the normal component is same. There is no change in the normal component, right? So what advantage I am getting? What is our aim for a sweep? We want to increase the critical Mach number, right? We want to increase, I repeat, we want to increase critical Mach, or M critical means critical Mach number. What is the critical Mach number? It is that free stream Mach number at which, for the first time, some point on the aircraft attains Mach equal to 1. Okay? So that is why if I give a sweep like this with the understanding now the aerofoil are stacked like this. Okay? So what happens? Even if the speed is like this, the normal component become V cos of this sweep angle. So now you could see free stream is V, but normal component to leading edge, provided the aerofoils are stacked like this, that becomes V cos lambda. So the local Mach number will be less than the free stream Mach number, and that is how we increase M critical. Okay. So now, if that is true, if we understand that, this is very important, and you should refer my first course, Introduction to Airplane, where I think I have clarified this thing. Now, let's see. Coming back to this, if this is the lambda, now if I am going for a side slip, that means you have seen this goes like this. Okay? It is going like this. So it was like initially like this, now like this. Okay? So what is happening? How much it is turning? It is turning by beta. Okay? So here the normal component will have V cos of whatever lambda. Lambda is the sweep angle. Because it has gone into, so it has reduced, whereas the normal component here that has increased V cos lambda plus beta. This is clear? If I do it like this, this is the airplane, and let's say this is the lambda sweep angle. Now, when I am trying to fly such that there is a positive beta, that means I will turn like this, so the relative airspeed is this. So this is beta. So it has turned into by angle beta. So this effective angle becomes lambda minus beta, whereas here it has increased by beta, so it becomes lambda plus beta. Clear? So the moment there is a difference in the normal component of V, you could see easily that this will be more compared to this because of cost function. So what will happen? The drag experienced by this part will be more compared to drag experienced by this part, because the velocity here is more. Drag is half rho V square. What is drag? Drag is half rho V square SCD. So V here is more compared to V here because of cost factor. So since there will be a larger drag here, okay, so this will generate a positive Young moment. Clear? Larger drag. So for the moment there is a beta, it will generate larger Young moment. So Young moment positive, it will try to discourage this beta. It will try to take it to beta equal to 0. And for our definition, for positive beta, it will give positive Young moment because the drag here is more. So we say wing with a sweep, C and beta will be stabilizing or greater than 0. Is it clear? I repeat here again, you have understood that if this is the light and the airplane is like this, and this is lambda, we are discussing about whether the wing will generate C and beta because of its wing platform, whether it will generate stabilizing or destabilizing. We say we have taken a swept wing, and when it is going with the beta, that means configuration should be like this. This is positive beta, and you could see here, earlier this angle was cos, the angle was lambda, so normal component was V cos lambda. Now what has happened? As it turned by beta, this angle has reduced by beta, so this become, normal component became V cos lambda minus beta, and whether it has increased, so this became V cos lambda plus beta, right? And since we know because of property of cost function, this speed will be more. This speed more means the drag on this wing will be more, and then that drag will give a Young moment positive, so it will generate Young moment positive for a positive beta. So for wing, the C and beta greater than 0, which is typically for the swept wing. And if I give you the expression, I will not derive it, or if you want, I can write the expression, and you should do it yourself to get the final result. So net yawing moment will be nothing but, you see, half rho V cos of minus beta. This half rho v square. Now v on the right wing is v cos lambda minus beta. So half rho v square. Then half of the wing SW by 2 I have to take. I'm considering for the right wing. And I'm assuming that whole force is effective at a distance, let's say, y bar. Okay? That typically like a centroid, the pressure distribution. So this is this half rho v square S, half rho v square S. Of course, you have to multiply with CD of the wing. Right? This is from the right wing, and from the left wing, it will be minus half rho v cos lambda plus beta square SW by 2 y bar in CD. So this is the net yawing moment coming because of differential drag between this wing and that wing. And then I will find Cn by dividing yawing moment by half rho v square SB. As I told you, you have to derive it, y by b beta sine 2 lambda. What I have done, this v cos square, if I just to give you a hint, please do yourself, don't expect everything will be, these are all class 10th standard. You have to expand it here by taking half rho, all this thing common SW by 2. So this can be generalized by using trigonometric relationship, and you will get an expression of Cn like this. So from here, you will get Cn beta equal to CD, y bar by b, and say sine of 2 lambda. What is the message here? Message is for a rectangular wing, which is having wing like this, you will not get any contribution towards directional static stability because of wing. However, if you can introduce sweep to this wing, right? Sweep in the right sense. Please understand, sweep means right sense we are talking about. So some aerofoils also will be something like this staggered. Then only this is a sweep. If you introduce a sweep, then you can get stabilizing contribution because of CD, right? And it will also depend upon how much sweep angle you have given, right? This is extremely important. Please realize there are now concept goes on vertical tailless aircraft, right? Because the moment there is a vertical tailless, you will think who will provide directional stability? But I say I don't require a vertical tail if I can give sweep to the wing, that itself will give me Cn beta stabilizing. So it's nothing very mystic about it. It's very straightforward from the basic understanding of flight mechanics. Right? So far we are talking about directional stability. Now we'll talk about directional control. You have seen our aircraft, and I have demonstrated you that for directional control, primarily we use rudder, right? Okay, to take a turn like this, we primarily use rudder. But please understand, all this motion can easily be generated using different combination of control surfaces. For example, I can use an aileron and still turn. All those things, complexities you will understand. But at present, I am talking about primary directional control, which is nothing but rudder. What was primary control surface for longitudinal control? It was elevator. Okay, and how we found out the control power? Remember what was the basis? If this is the horizontal tail, this is the elevator. We will see. First, we will define what is delta E positive. This is longitudinal, right? And what was the understanding? Understanding was, let us find out how much alpha of the tail is changed because of elevator deflection, and which we denoted by tau, and then we see how much delta L will come because of this deflection. That will be half rho v square at the horizontal tail, or tail into S tail into CL alpha tail, and into whatever this is coming, that is tau into delta E. So that was the change in the lift, which was here. I repeat here for longitudinal case, we knew d alpha t by d delta E is tau, that is how much alpha tail is changing per unit deflection of tau or deflection of elevator. And then what we did, for a given elevator deflection delta E, tau into delta is the change in the angle of attack at the tail. So I know half rho v square st cl alpha t into that change in angle of attack will give me delta L, and from there I can find out what is the control power or not. Similar thing we will do for rudder also. Okay. Similarly, we define tau for vertical tail as d beta at the tail by d delta r. Okay. So if I am deflecting, say this is the, I am looking from the top. Okay, as per the convention, this is looking from the top. Please understand, this is the positive delta r towards left, and this is the negative delta r. Let me explain this. Convention wise, if this is the vertical tail, or let me more illustrative, if this is the rudder part, okay, then towards left, this is the positive delta r. And towards right, it is the negative delta r. Is it clear? Towards left, positive delta r. Towards right is negative delta r as the convention. Now see what happens. If I am giving a positive delta r like this, so the force, I am going forward also, the force on this vertical tail will act which way? I am going like this, so force will be in this direction, right? Which is in the right y direction, so positive force will generate. However, the yawing moment will be which way? Force is here, CG is there, so yawing moment will be left wing going back. It is something like this. So positive delta R, you could see here, is generating a negative yawing moment, right? That you should remember. If this is delta R positive, then what I will do, I am trying to calculate, we are trying to control rudder, control power. We are now expert because we know how we calculated here. So what we will write is yawing moment because of delta R positive. What is delta R positive? Delta R positive means, I have shown you that the rudder going towards left as I am flying like this. This will be equal to force. Force means half rho v square at the tail, S tail, then LV into what is the beta change because of delta R? We know tau v means d beta by d delta. That means per unit change in the rudder deflection, how much beta at the tail is changed. So if I multiply delta R into tau v, that will give me what is the change of beta in the vertical tail. So I will multiply this tau into delta R, okay, and beta into cy beta will be the force, and force into this length is moment. Is it clear or not? If I try to again explain you, I can write it like this: half rho v square at the vertical tail, S vertical tail. So I will take out SV, LV into, I will not write LV here. This is half rho v square S. This is into cy beta, okay? Into beta is nothing but tau into delta R. So this whole becomes the force into LV, that becomes the moment. Is it clear now? What I have done? I have this tail, I make it vertical tail, dynamic pressure at the vertical tail, no objection. S vertical, no objection. Cy beta into beta should be the force. So like CL alpha into alpha tail. So Cy beta into beta, beta is what? Tau into delta R was the additional beta because of delta R deflection. So this becomes the force into LV is the moment. So this gives yawing moment. What do you have to check? You have seen that if delta R is positive, it should give yawing moment negative because the force is in this direction. Yawing moment will be negative. So I have to check whether it is giving yawing moment negative or not. These are positive. Yes, Cy beta is negative, you know that. So it is indeed consistent in sign. So from here, yawing moment expression, I go to Cn. How do I go to Cn? I divide by yawing moment by half rho v square. So Cn I write as yawing moment divided by half rho v square S into B. So Cn I will get as neta, vertical tail, then HV by S, LV by B, no problem. Then tau Cy beta delta R. Let me check, everything is there. Half rho V square, so divided by half rho V square free stream, so it becomes neta SV by S, LV by B, tau, okay. And I am again checking that if delta R is positive, this varying moment should be negative, that we have seen physically, and since Ui beta sign is negative, so this is taken care. We are talking about control, so what is Cn delta R? That will be neta V, SV by S, LV by B, tau into Cy beta. And what is the sign of Cn delta R? This is less than. Because Cy beta is less than 0, because Cy beta is less than 0. Now recall, let us go back to longitudinal case and directional case. Let us make one comparison. See, for static stability, what was the condition? Cm alpha should be less than 0. So what is the condition for static stability for directional? Cn beta greater than 0. So for trim, what is the condition? Some alpha positive, or we say Cm naught greater than 0. For most of the directional case, trim is beta equal to 0, so Cn 0 is 0. Right? What about the control? Cm delta E was less than 0, and here also Cn delta R is less than 0. That sort of a mapping you must have. Okay? Let us ask a question. Why we are getting involved into so many expressions? Directional stability, directional control. Please understand, when we are discussing about longitudinal stability and longitudinal control, we got this insight in an exhaustive manner that I may like to fly at different CL or different speeds. I may take to turn. I may go for a maneuver. I have to go for takeoff and landing. So all these things are to be appropriately understood. For that, we did elaborate study on static stability, static margin, elevator control power, neutral point, etc., etc. But why we are doing all this directional stability and directional control? Because primarily, you understand, with our rudder, the specific role is powerful enough to handle adverse yaw. I will explain what is adverse yaw. Then it should be able to asymmetric power. I will explain what is it. And third is crosswind. Then fourth, spinning. The menu will come. What is an adverse yaw? As I told you, if I want to go for a bank, a roll like this, okay, and let's say positive roll, and a roll like this. Roll positive by convention is right wing going back. Okay. What is happening? If it is going like this, you could see that this portion, the relative wind will come upward. You know? As it's going like this, the relative will come upward. So here, the angle of attack will increase compared to this, which is going up. And angle of attack increase means lift will increase. Lift increase means induced drag will increase. As the induced drag increases here, it will try to turn like this. So if you want to go for a roll, it will automatically turn like this. So that is called adverse yaw. And we do not want to do that when you are going for a banking. So this adverse yaw has to be controlled, neutralized by using appropriate rudder deflection. Because rudder can give yawing moment in either direction, depending upon where you have deflected. So this is one of the primary purpose of rudder. We will also see one of the purposes on asymmetric power. That is, suppose there is a twin engine airplane, one engine here, one engine here. And one engine fails, then what will happen? The moment one engine fails, this will generate a yawing moment because of this thrust being alive. So I have to neutralize this. How do I do that? So because this thrust will be generating yawing moment in this direction, I have to generate a yawing moment in this direction. Who will generate this yawing moment? This is through a rudder, by appropriately deflecting it. Okay? Which way I should deflect? I should deflect the rudder, you know by now, deflect like this. This is rudder positive. If I deflect like this, it will generate a force in this direction, so that will give this moment which is required to nullify this moment. So rudder is extremely important. So rudder control power should be assessed. It should have enough control power so that it should be able to handle this sort of asymmetric power if there is a failure of engine. Right? Similarly for crosswind, what happened in crosswind? I want to land like this, and because of crosswind there is a beta introduced. So how do I land holding this crosswind effect? That also will be explaining as we will be going forward. But you understand, rudder is required here. Spinning, sometimes the airplane during spinning may go to a stall. Stall is, as the angle of attack may increase very high, your aileron, etc., may not be that effective because the wing has stalled. But rudder can be very effective, and that rudder can be used to stop this rolling motion, or it can help us in taking out the aircraft from stall. So these are the things we will be discussing, but you should know that rudder has specific purpose for handling adverse yaw situation, asymmetric power, crosswind, spinning to bring out the aircraft from stall, and there are many such will come. So as I'll be completing the lateral, then we'll address them in an appropriate sense, in an appropriate time. Okay? We are trying to give an example of importance of rudder control. Why you should know this? Why you should not only know how it works, but you should know how to design an appropriate rudder. For a specific case, suppose there is a twin-engine airplane, and one engine has failed. Let's say this engine has failed in flight. What will happen the moment this engine fails? This thrust is there, so about CG, it will give a yawing moment. What sort of yawing moment? Sign will be positive or negative. You could see it will turn like this, so this right wing going back, so it will give a positive yawing moment. So how much yawing moment it will give? It will give T1 into A. This is the force into distance. This is the yawing moment it will give. Now what is happening? I need to correct this yawing moment, otherwise the airplane will rotate. So what I have to do? I have to give a rudder deflection to counter this. To counter this, I have to apply rudder. So this is giving moment in this direction. So I want a moment in the opposite direction like this. So how can I get that moment? I get the moment if I deflect the rudder in a positive sense. Delta R positive. The moment delta is positive, I know this force, this will give this moment. And how much moment rudder will give, which is yawing moment rudder will give, will be given by this expression, half rho v square S B into Cn delta R into delta R. Right? We know the expression of Cn delta R by now. So these two should be equal in magnitude. Right? By equating these two, I can easily find out how much delta R is required for a given T1. Is it clear? I'll equate. This is the disturbing moment. This I equate with this. So I can easily find out how much delta R is required for a given T1. And then I should also know the limitation of delta R, how much delta R I can deflect for it to remain effective. Right? So for a particular value of Cn delta R, the delta R is very high, so I'll increase Cn delta R so that delta R value remains within the limit. So this is a very simple but very interesting and very useful approach to ensure that you can still control the airplane when one engine has failed as far as directional motion is concerned. Right? Thank you very much.